这个报告嘉宾呢是Professor Roman. Let me introduce Professor Roman. Professor Roman is a full professor in the Department of the Physics at the University of Manchester in the United Kingdom and a researcher at the National Graphene Institute. He has been engaged in the preparation, electronic transport, and optical studies of heterostructure of two-dimensional materials for a long time. Using inorganic assisted heterostructure preparations and ultra-high vacuum technology, he can achieve automatically clean large area heterostructure of two-dimensional materials, providing a platform for the observations of a wide range of physics phenomena. Professor Roman has published 36 papers in the journals such as Science, Nature, and their sub-sister journals, with 7 of them being cited over 1,000 times. So his topic is structure reconstruction as an ultra-clean interface of the two-dimensional materials. Now it's time for Professor Roman.
Hello, I'm very glad to be here, and I would like to thank the organizers for giving me this wonderful opportunity to speak to you. It's not very often that we speak to this part of the world, even though that this part of the world is now more important than the rest of it in terms of nanofabrication and technology. So I lead a nanofabrication group in this building, which is, National Graphene Institute in Manchester. It is a huge institute where we mostly deal with TRL 1 and 2, so fundamental research and prototyping and proof of principle studies. The group has 3 different directions that we're working on. So one of them is nanofabrication of ultra-clean heterostructures. Why nanofabrication is important? Because it has been the bottleneck, critical bottleneck in both fundamental science and technology and applications for 2D materials. The reason we don't have mobile phone with transistors and graphene and TMDs is nanotechnology. It is still lacking and it needs to be developed. The second direction is so-called twistronics, where we twist 2D materials and study the interfaces. And the third one is transmission electron microscopy of liquids. So that is, I'm not going to cover this today. It's a big direction that is out of the scope. But shortly we make these nanoscopic bubbles and we study chemical reactions in situ and TM. So graphene started with very high electron mobilities. Back then it was huge. It was only 10,000. Now we understand how little it was. And then a few years later, after the discovery, people started suspended graphene, and you can see that the mobility drastically improved as the quality of graphene improved when you remove the substrate. And then a few years later yet, Columbia University managed to produce graphene on boron nitride. And that was a critical step where we put graphene on atomically flat and clean substrate. We see dramatic improvement in terms of the mobility of the devices. So currently at low temperatures, we hold the record of 10 million, but I'm sure it can be improved in the near future. So if you look, for example, compare this with gallium arsenide technology, it took people over 30 years to get to this point. And we had, from 2004 to 2010, when people transferred graphene and boron nitride, only 6 years. And this is all done on tabletop. So it's such a easy technology, such an easy way to make samples with ultra-high mobilities. However, the problem is that this technology is scalable. It is wafer scale. And graphene, we're basically playing with 10 micrometer devices. So how do we improve it and how do we make it better? The key for the 2D materials is that we can really mix and match different layers, and we can produce this layered heterostructures without really caring whether they like to grow on top of each other or not. Because there's a mechanical transfer and we grow them separately or exfoliate them separately, we don't need to worry about the chemical matching and matching of the chemical conditions. And that really opened a huge field, which is blooming and expanding even now, so many years later. And the key really is that you can take, superconductor and topological insulators and look at the interface of the beautiful physics in between without really spending years to learning to grow this kind of system. And the idea, again, is coming from the molecular beam epitaxy, where you can grow these materials layer by layer. Only now you have much, much greater space to explore because you have so many more materials and you don't need to worry about lattice matching in the growth. So how do people build these layer structures? They take individual layers. They can be exfoliated or they can be grown. And then they use clever polymer transfer techniques to pick up these materials and move them on top of each other and build these layered stacks. Today, there are kind of two key techniques. One of them is using very thin membranes of typically PMMA polymer, and the other one is called stamping, and it's using PDMS with another polymer liner on top. The reason we use PDMS is that PDMS is quite dirty, but the real key is that when you stack these materials and you look in, for example, AFM, you see that a lot of area is atomically clean between them. And this is where we get the high mobility. But in between, there are these bubbles and pockets of contamination. And that is the problem for the scale. We cannot scale if a lot of the area is contaminated with these folds and pockets. But we can do beautiful fundamental science if we only focus on the areas in between, on the clean and nice areas. And so there are also a lot of materials where this kind of cleaning process, self-cleaning, doesn't happen. So you transfer them together and all the contamination that have been trapped in between stays trapped in a continuous layer. A lot of materials like, for example, copper oxide superconductors or mica, they remain relatively unexplored in terms of heterostructures because we simply cannot make them form these beautiful clean interfaces. There is a whole lot of research, hundreds and hundreds of papers on how to transfer 2D material layers. And it's really important. You can see here just a small selection of these papers with key techniques on how to produce the clean interfaces. I put the reference here to acknowledge them, but I'm not going to stop here for long. The key really to making cleaner structures is higher temperature and slower interface collapse. So when you put these materials together, you're basically trying to collapse them as slow as possible. And as you collapse them, you squeeze out all the contamination that have been building on the surface. And because everything is done in the air or in argon, there is a lot of hydrocarbon contamination and gases on the surface that is being trapped. And we're kind of trying to just squeeze them out when we do that. So with this technique, back in 2010, we were looking at these pockets and we were looking what are they made of. And really the key, what we've achieved is we took a focused ion beam, we cut a slice out of the sample, we put it in transmission electron microscope, and what we see at the interface is individual layers, right? So this is, for example, graphene boron nitride, and you can see that there is nothing in between them. They are pristine and atomically clean. So that was a huge surprise for somebody who does, for example, material science or vacuum technology, that in air you can make something atomically clean like this. However, later we found out that these pockets, they are basically full of hydrocarbons, which is organic molecules that floating in the air all the time. They are produced by us, by polymers, by plastics, by cars, and all of that is being trapped between the layers. So the next stage in technology was trying to put this in a very clean argon chamber. It is, in terms of vacuum, not very clean. It's compared to 10 to the minus 4 millibar vacuum pressure, partial pressure of water and oxygen. So it's not compared to the UHV very good, but it gave us a lot of space to explore, especially those materials that are air sensitive. So it turns out only about 10 materials are stable in the air, and if you want to explore more, you need to really take care of the environment you're making the samples in. And so doing this in argon allowed us to make a lot more different heterostructures, particularly with TMDs. And you can see here, this is a cross-sectional image. You can see individual atomic planes. And when you stack an argon, you can see that the planes are much closer together because there is no contamination in between pushing them apart, and there is no damage from the air introduced into tungsten diselenide in this case. So Glovebox really moved the field for another 5 years, and then we reached to this point where we now have a lot of other materials like magnetic materials, trihalides, which are too sensitive even for Glovebox. So we basically reached another big problem where we really, really need to go to ultra-high vacuum. And so here's a short summary with all these polymers that you can, you can use and you can distribute to your students if they're learning to do this technique. But yes, so in short, we need argon if we are working with very sensitive materials. We are transferring very slow and at high temperature as possible to remove the contamination. And then polymers that we're using for all of this is really the key limiting factor because you cannot heat them, they melt. You cannot put them in vacuum, they outgas. You cannot treat them with plasma, they etch. There is not so many things you can do with polymers, and we need to move away from polymers as a field in general. And so what we've been working in the last 4 years, maybe even 5, is trying to transition away from polymers. And the system we chose was silicon nitride. Silicon nitride membranes are extremely mechanically strong. Now, before the 2D materials, it was one of the strongest thin layers you can ever make. And they have wafer scale grown, so potentially scalable, but they don't stick to 2D materials. So how do you go about that? What you do, you deposit a thin layer of metals, 3 different layers, 3 different metals. Again, I'm not going to go into detail why we do this, but gold here is the key. Gold is the glue that picks up to the materials, and by controlling this thickness of gold, you can control the adhesion between 2D materials and this membrane. So if you put, for example, 0.1 nanometer, nothing will stick. If you put 1 nanometer, everything will stick, but then you cannot get it off. And silicon nitride is extremely high temperature stable. You can put it in ultra high vacuum. You can put it in all kind of corrosive liquids to clean your samples. And it is more mechanically stable. And so the idea is really simple. For research, for small structures, we use this cantilever shape, which is similar to AFM style cantilever, only it's a lot wider and a lot longer. And we basically just touch our crystals with this cantilever, and then we pick it up and we move to another one, assemble step by step, assembly the same way as we've been doing this with polymers, only this time it is a lot faster because now we can use it at a very high temperature. We can put up to 300, 350 degrees, and you can see this is like a live recording of a stacking, and we don't really control the speed of lamination. We don't really worry about all of these problems with polymers. It become a lot easier to do. What do we get with this technique? So we have been working with exfoliated flakes traditionally, so we've been experimenting with those. And here you can see a graphene device which is 50 by 50 micrometers. This is at the moment our biggest device, but it is comparable with exfoliated size. So you don't get graphene much larger than that. And in this graphene, 50 by 50 millimeters, you can see the typical mobility. So this is a carrier mobility versus concentration, and you can see values of about 10 million at helium temperatures. So as I said, at the moment, this is the world record for graphene quality and graphene size. And really, if we transition to CVD and we can make millimeters, I'm sure we can beat gallium arsenide and we can go a lot larger than that. But how about more tricky layer stacks? So here is a band diagram of a device which we called LED, light emitting device. And the basic principle is that you have a semiconductor like TMD in the middle, and then you have 2 graphene layers separated by tunneling barriers. You inject electron from one graphene, hole from another graphene, they recombine inside of TMD and produce photon. So this is basic electroluminescence. This is a layer sequence, so you can see this one is already 7-8 layers thick, a lot more complex. And here you can see AFM of such device. This one is about 25 or 30 micrometers. There is not a single contamination pocket. And the electroluminescence map looks extremely homogeneous compared to all previous works. And in fact, if you put it next to the polymer assembled, so these 5 are assembled with polymers with different types of stacking, different temperatures, and this one here is assembled with these cantilevers, and you can immediately see how much cleaner they are in terms of topography and the amount of interlayer contamination. Now, what that also allows you to do, it allows you to transfer any 2D material that we found so far is working with this technique. You can transfer pattern materials. For example, you can cut these little gears and transfer them with cantilevers, and you can do submerged transfer in liquids. So this one is done in acetone, which swells or dissolves polymers. So you cannot use this with polymers, but you can use it with silicon nitride because it's chemically inert and nothing happens. And you can also make suspended structures if you make little holes in your cantilever. So there is a lot of scientific room here to explore and do wonderful devices. However, even more importantly, scalability. So can we scale this, and how do we scale this? And the key here is to use a polymer as a support. So this is a PDMS that we just discussed. But this time we put silicon nitride on the surface, and that silicon nitride is a perfect barrier for all the contamination contained in the PDMS. So this way we have both clean interface, and we have a well-supported and pliable substrate to hold the 2D materials. And one example we've made here, this is tungsten sulfide monolayer on a few layer tungsten sulfide grown on sapphire. And this is millimeter scale samples. We are trying to scale this up at the moment, but this is work in progress. A lot really depends on the supply of 2D materials, and if you can find a really nice monocrystalline uniform monolayers of TMDs, it's a lot easier to make this technology happen compared to the normal kind of state-of-the-art polycrystalline material you buy. And so the most advanced step that we took is putting this whole technique into UHV as an ultra-high vacuum. And so here you can see a brief sketch. This chamber is about a cubic meter large, and it has all of the stacking stages. I think it's in total 11 stages inside that manipulate, exfoliate crystals, and they stack them in ultra-high vacuum. And if you choose to do polymers in UHV doesn't actually help. Well, it helps a little bit, but you can still see bubbles if you use polymers. And that is because polymers, they produce this contamination continuously, and you cannot really clean them no matter how long you pump them for or how well you anneal them. And so really, if you're planning to use polymers, there is no way to go to ultra-high vacuum. You need to switch to inorganic technique, such as silicon nitride, and this is where we really this is the latest data that we get. We have this large graphene on graphite, so this is a twisted structure, and you can see the more lattice produced. This is conductive AFM imaging with almost atomic resolution, but the uniformity of this twist angle or strain across a device of 20 micrometer large is basically 10 times better than all previous studies on a scale of 1 micrometer. So we both increased the lateral scale by an order of magnitude, and we increased in homogeneity of the strain by about an order of magnitude, simply by doing this in vacuum using these cantilever techniques. So really, for people who study twistronics and look into twisted physics, this would be a great technique and a good solution to the problems of all this contamination and bubbles. Now, just to say a few words about the superlattices. So here's the basic superlattice with graphene and boron nitride. I'm sure you're familiar with this, but in very short summary is when you put materials with similar lattice constant on top of each other and you rotate them, you can see this superlattice appearing, super period. However, it's not that simple, because when the lattices are very closely matched, there is more favorable regions here in terms of energy and less favorable regions. And what happens is that they sort of click into perfect alignment locally. It's much easier to see on one-dimensional kind of plot. So you can see here, this is potential created by the substrate, and here we put this atomic layer of materials. So instead of sitting like this and commensurately, they really would like to sit commensurately to decrease their adhesion energy. And what they do to solve this problem, they strain locally to sort of click into the underlying lattice. And the excessive strain produces the boundaries between these nice and perfectly clicked regions. In fact, you can see this if you do, for example, piezo AFM, you can see these lattices quite clearly. However, for this technique to work, your sample needs to be exposed, so you cannot encapsulate your sample with HBN, for example, and visualize the Mora pattern. Now, if you have encapsulated it, you can still go for electron microscopy, and there is this technique called secondary electron channeling microscopy, where you basically put your sample in an SEM, and then you tilt it at a specific angle of about 22 degrees, and you can suddenly see the domains appearing. And that is because the electron penetration through this crystalline solid is different for different domain structure, for different crystalline structures. And that is immediately obvious when you look at this picture. So this is one of our samples. There is a published work earlier, which is cited above, where you can find this. And so if you start using these techniques, okay, there is also, of course, TEM, so you can look at atomic resolution, and you start visualizing these domains. In graphene, it's actually very simple. In graphene, you have triangular domains of different stacking. The period changes with the twist angle, so it's quite, everything is straightforward. In TMDs, it's a lot more complex, because now you have no inversion symmetry, and you have two possible orientations. And these are so-called parallel orientation, where the unit cells are parallel, and anti-parallel, when you basically rotate one layer 180 degrees relative to the other. And what I'm going to show you briefly is that these are producing completely different quantum systems. So this is freedom that is given to us by twistronics in terms of exploration of really quantum physics and low temperature physics. And so if we twist them at very high angle, for example, 3 degrees or 2 degrees, you don't really see much happening. So you have this periodic modulation of the atomic registry. But if you go for smaller angles, you start seeing these commensurate domains that are basically a perfect bilayer. But it is only, say, 10 or 20 nanometer island of perfect bilayer. And in between, you have the boundaries. So the reason it is forming is because 2D materials really like to click into each other in terms of energy favorability. And if you plot adhesion energy as a function of different stacking orders, you can see that really the lowest energy you have is for 2H stacking. And this is the stacking 2D materials usually grow in when you grow in the bulk, because it's the most favorable. But there are others that you produce that don't grow naturally. For example, this domain here. So this is metal on metal. It corresponds to the alignment of atoms in top and bottom layer. And this is the least favorable domain. And of course, there is this point here, which is unfavorable, and it doesn't form a domain at all. But what happens is that this kind of texture dramatically changes the properties of the system. And as you go from large twist angles to small twist angles, you can see that one of the domains expand. So you turn your system into bilayer, 2H bilayer TMD, but you have little grains of MM. And these little grains of MM at low temperatures form quantum dots. So what you create a network, a periodic network of quantum dots that are controllable. Their exchange and their interaction is controllable by the twist angle. And this is why it is such a flexible structure, flexible platform for exploration of quantum physics. The reason you have quantum dots appearing is because of the strain. So when the lattices click, they do it by creating strain. And strain in piezoelectric materials creates piezoelectric charge in the lattice. So that charge gets screened by free electron carriers, and that is why you're creating little quantum dots locally. There is a whole lot of papers about beautiful optical properties of this system. I'm not going to touch that, but there is so much research and very high impact papers on this. This really is an interesting system and worth looking into. Now, if you look at the parallel alignment, What we see now, we see two equivalent domains, but they are not the same. So the stacking looks very similar, and the energy of the stacking is actually the same. So here, the two curves overlap in terms of the energy, but they are mirror reflection of each other, and they don't have mirror symmetry. And what that means in kind of physical terms, right? Because you don't have mirror symmetry, you can now have a wave function that is asymmetric with respect to the two layers. So for example, if you take a conductive state at the bottom of the conduction band at Q point, this state will be more based on, for example, top layer than the bottom layer. And in the opposite domain, you have this state sitting on the bottom layer and less on the top layer. So if you do tunneling experiments with conductive AFM, you see a huge difference in tunneling current because these are the states you would normally tunnel to from the conductive tip in AFM with a specific metal. So that is kind of a quick illustration, but if you go a little bit deeper into this, it turns out that this is not just a single wave function being asymmetric, it's entire electron density being asymmetric. And in fact, if you kind of plot this and calculate DFT for the electron density, you will see that in here, there is, in between the layers, there is a charged capacitor, which is electron density and a hole density accumulated due to the symmetry, due to hybridization of the conduction valence band. And this is ferroelectricity in principle because you now have electric polarization, which is pointing up for this configuration and pointing down for the opposite configuration. So half of these domains will be polarized up, and then other half of these domains will be polarized down. Now, if you apply an external electric field and you monitor this domain map with electron microscopy, just like I showed before, you can see that as you apply the field, the dark domains shrink, and then if you reverse the electric field, they expand, and you have a hysteresis. So it is in terms of classical definition, this is normal ferroelectricity. However, it is now sliding type. So it is purely two-dimensional ferroelectrics that is formed at the interface between 2D crystals. And again, this is a very popular topic right now. There's a lot of papers being published on this. And so this is our contribution to this. You can see that small domains, for example, they sort of inflate and deflate, but the junctions, these middle points, they don't move because there are three domains on each side of that point, and the forces are compensated from three sides. So these nodes, they don't actually move when you start to switch these devices. And this is quite critical for example, if you want to make an applied ferroelectric junction out of this material. You can, of course, see this by KPFM. So if you measure surface potential, you can see the variation of surface potential, and this value is about 120 milli-electron volt. So that is room temperature ferroelectricity with a very decent value of the potential that you can easily see without any super complicated equipment. It is quite robust, and it works up to at least 400 Kelvin and probably a lot higher than that. And so, okay, so what if we try to construct a device out of that and make a ferroelectric tunneling junction? So this device is actually used in industry with classical ferroelectrics. Can we do this in 2D materials? And the answer is yes, but everything will be different. And the way it is different now is that you do have this electric field inside that changes the way electrons tunnel through this dielectric layer. And depending on the polarization orientation, up or down, you can have either high tunneling current or low tunneling current. So at the moment, we have aspect ratio of 10, but this can be improved further with design of the contacts and dielectrics. But that's not the issue. The issue really is that if you want to try different configurations where your tunneling junction is covering different domains, right? So here it is covering little triangular domains with a large twist angle. Here it is covering a sort of two-domain walls. You don't see the switching works differently. So this switching, for example, is more suitable for neuromorphic type devices because it is in essence a resistive switching. And if you have just a single boundary in your tunneling area, when you apply the field, you can completely expel it out of the junction. And that means that you have quite a large offset in your tunneling, and that is more like a classical ferroelectricity. So already by just putting these devices in different place of the twisted lattice, we have different functionality that can be used in a different way. Controlling this and making it wafer scale is a separate issue, and I'm not going to touch into that. But there is a lot of promise in this kind of devices, and keep in mind that these are very high, highly optically active systems. So all of this would change excitonic behavior. This switching is not just electric, it is also optical switching, because associated with ferroelectricity, you also have an exciton sitting there, which is polarized up or down because of the ferroelectricity. And so by switching these domains, you're also switching the energy of that exciton inside. And so I foresee in the future there will be a lot of interesting devices where people combine optical measurements and ferroelectricity and try to do this kind of hybrid functionality. And so just to summarize, so in terms of twistronics and TMDs, there are two very different systems, and that is where you align your layers either parallel to each other or at 180 degrees. In one case, you achieve a controlled network of quantum dots. And again, there is a lot more papers recently on this topic. And in the other system, you achieve a system with broken inversion symmetry, where you have ferroelectricity, where you have polarized wave functions, and that can be really employed in some high-end electronic applications. Now, what is the problem? So the problem is, of course, twist angle, because if you go and make a twisted device in a lab, you will probably see something like this. You will see a lot of cracks, a lot of bubbles, and really you cannot move on with this into applications until you solve the problem of homogeneity. And this is why the bubbles and the cracks and the transfer technique is really the key to progressing this high-end optical and electronic applications. We all know that there is a lot of applications of 2D materials in lower tier technologies where you don't need such a uniform and clean system. But if you're really looking towards telecoms, if you're looking towards quantum computing, sensors, you would really need to achieve a very high uniformity and much better transfer techniques and much better growth techniques. So here's a paper doing this with, they measure disorder of the quantum of the twist using squid on tip. So it's a quite elaborate technique, but what they get is 0.1 degree. And this is the image of this 0.1 degree disorder in terms of local twist. And you can see that there's a variety of different domain structures that all behave differently. So what is the way forward? Well, as I said, I think UHV is really the way forward for this technology. So this is our huge system, which costs £2.5 million, now nearly 3 with all the upgrades. But it is designed to really do stacking in ultra-high vacuum. At the moment, we're talking about scale of 1 inch, but hopefully we will be able to expand in the near future to something larger. And we do have complete removal of hydrocarbons, and we do have a lot more uniform interfaces and a lot more uniform twist angle picture in this. So with this, I'd like to thank you. These are the people who did most of the job. Oh, no, disappeared. Right, there you go. And of course, we're collaborating with Theory, with electron microscopy groups, and KPFM in NPL. Thank you very much.
Okay, thanks for a wonderful talk. And now we open for several questions.
Thank you for your talk. So I have actually several questions. The first one is you actually use silicon nitride to transfer. I guess it's also because it's stiffness, right? Then at a certain point that you said you can transfer larger area by using silicon nitride membranes. So how did you fabricate these membranes, and will that also affect you?
So these membranes, that's actually a very good question. The way we produce them, we buy a wafer. It's a silicon wafer with low pressure CVD grown silicon nitride on the surface. And you can buy different thicknesses. You can buy 100 nanometers, 500 nanometers, micrometer. And then you put it in KUH and you remove the wafer, and silicon nitride is left. So you basically dissolve silicon and KUH as a wet etch process. And then by doing lithography, you can define the size of the window you etch or the shape of the cantilever you create. So this is, optical lithography combined with wet etching, standard wet etching techniques.
Will the flatness of the surface affect this transfer?
Oh yeah, absolutely. So this is why it took us 5 years to get to get here. It's not just flatness. When silicon nitride grows, it often grows with strain, meaning that if you release it, these cantilevers can curl up into a little scroll. And so you need to find a source which is not strained, low strain silicon nitride. And then, yes, of course, flatness is a big issue, but you can do mechanical polishing on this wafer to just make it flatter if it doesn't grow flat enough from the beginning. But you can also find suppliers which provide very flat material.
Okay, last short question. We know that the strain will affect the device's performance that very much. And by using this silicon nitride, actually you might, I guess, or you might create more strain than using polymer, right?
Actually, no. So we see completely opposite, because the problem with strain is really thermal expansion. Because when you heat these materials, especially PDMS, the thermal expansion is huge. And at that point, when you're transferring and you're applying heat, you strain your materials, and that happens randomly because polymer is amorphous material. It creates a random strain map in your 2D material. Now, if you go for inorganic materials, usually the thermal expansion coefficient is at least 10 times lower for all inorganic materials. And silicon nitride is quite low on the list. It's very close to 2D materials. So they're much better matched in terms of thermal expansion, but it is also mechanically a lot stiffer than polymers. So it's very hard to actually take and strain the silicon nitride without breaking it.
Thanks.
Okay, there's some other question?
Thank you very much for your presentation. I'd like to ask, what's the smallest scale you can transfer the membrane? Because I know some single crystals are very small. They can't be made to like very big size. Is there a limit to how small the membrane transfer?
So there is no really limit on how small. I mean, normally we will work with tens of micrometers, but if you have something less than a micrometer, it would still transfer. Okay. I don't think it's a problem. I'm not sure if you're talking about 10 nanometer quantum dots and little islands, you may have some issues there, but because you have gold and you can adjust the thickness and adhesion of gold, you can really control how well you pick up, how sticky the surface is to 2D materials. So if you find that for a specific system it's not sticky enough, you can just put more gold, and then it can pick up. Yeah.
Okay, thank you.
Okay, let's thank Professor Roman for a wonderful talk.